Hello students, welcome to our today's lecture that is based on chapter 1st of physics class 12, electric charges and fields. So this chapter is related with the branch of physics that is electrostatic. Let's see what is the meaning of electrostatic or this branch. So electrostatic deals with the study of forces, fields and potentials arising from static charges. So what are static charges? The charges which are at rest position when we study the forces, fields, and potential arising from that rest position charges. This branch of physics is called as electrostatics. So what are electric charges? Electric charges is an intrinsic property. That means fundamental property. Intrinsic property of material, just like mass. Right? Just as mass is a fundamental property, electric charges are also fundamental property of material. We will see experiment in next next slide. So SI unit of charge is Coulomb. There are two types of electric charges present, that are positive and negative. Let's see the forces present in between these both charges. When we observe that two positive charges are kept together, right? Or two negative charges are kept together, what will you observe? That they both tends to repel each other. That means like charges always repel each other. You will see an arrow here and here, that when we bring two positive charge or two negative charge close to each other, they both will repel each other. Whereas opposite to that, opposite charges, that means unlike charges, one positive charge and one negative charge, if we bring close to them, what will you observe? That both will attract each other. That means there is a force of attraction between unlike charges and force of repulsion between like charges. So this is the experiment which will show us that how any material can get charged. That means we can say that glass rod is positively charged, but how it will get positively charged? So let's say there is a plastic rod and fur material. If we rub both of them, what will you observe? That that plastic rod will become negatively charged. How will this happen? When you rub fur on plastic rod, some of electron will get transferred to plastic rod, and that is why the number of electrons on plastic rod will increase as compared to number of positive charges. So we can say the plastic rod is now negatively charged, whereas the fur is transferring its electron to plastic rod. That is why electrons will be deficit from fur, and fur will become positively charged because number of electrons will be now lower in fur. Same experiment can be performed with glass rod and silk cloth. When you rub glass rod with silk cloth, what will you observe? That some of electrons are getting transferred to silk cloth from glass rod. So that is why glass rod will become positively charged, whereas silk cloth will become negatively charged. So in nature, all the materials are exist in neutral form. That means every material has equal number of positive charge and equal number of negative charge. But when we make something or we do some experiments in which the charges will transfer, so by these experiments we get some charge bodies, and that force, this mysterious force, is called electric force. Let's see some properties of electric charge. The first of them is charge is quantized. What is the meaning of word quantized? That means it is available in fixed amount. The charge of any object is always an integer multiple of elementary charge E. You can say charges are quantized, that is nothing but they are available in a fixed amount, and that fixed amount is nothing but n multiplied by E, where n represents number of electron, E represents charge on elementary particle, that is nothing but the charge of electron, which is given by 1.6 into 10 raised to minus 19 Coulomb. So charges are never exist in frictional values. as n represents integer. It may be positive, it may be negative. So we can say the lowest possible charge is minus E or plus E. After that, twice E or minus twice E. It cannot be possible that charges are 2.5 E or 1.7 E. So charges are never exist in frictional values. Next property is charges are conserved. Whenever we heard this word conserve, the only sentence that comes into our mind is that it cannot be created nor be destroyed. It can only be transferred from one to another. So yes, that is nothing but charges are also conserved. That charges cannot be created. They cannot be destroyed, but they can transfer from one to another. We have seen the example of glass rod and silk cloth or plastic rod and fur. In that we have seen earlier they were neutral material, but after rubbing them, that is nothing but we are transferring electrons on protons, right? So when we transfer electrons from fur to plastic rod will become negatively charged, whereas fur will become positively charged. But before that, they both were neutral in nature. The another statement for the same property will be the total electric charge in an isolated system remains constant. What is isolated system? A system through which there is no exchange of energy. It can be heat energy, it can be electrical energy, it can be thermodynamic energy. So when there is no exchange of heat in that system, this system is called as isolated system. So for isolated system, the total electric charge will be always constant. And charges are additive. That is, the total charge of a system is the algebraic sum of all the individual charges present in that system. For example, this is an isolated system. There are number of charges. Simply, we will just add all of them and we will find out the total number of charges of that system. Now, electric force and Coulomb's law. That is very important law. What are electric force and Coulomb's law? Let's see. If we consider two charges, let's say both are positive charges, both are denoted by Q1 and Q2, and distance between them is R. Let's say the distance between them is small r. So what will you observe when you keep charge Q2 near charge Q1? That Q1 will exert some amount of force on Q2. That force is repulsive force, of course, because these both are like charges. So they tends to repel each other. So this Q1 will exert some force on Q2, and that force is nothing but electric force, or we can call it as Coulomb's force as well. The formula for this force is K into Q1 Q2 upon R square, where Q1 and Q2 represents charges, magnitude of charges, and R represents distance between them. And K represents Coulomb's constant. This force law was first studied by Coulomb in 1785, and that is why it is called as Coulomb's law. That constant K has a value 8.98 into 10 raised to 9 Newton meter square per Coulomb square, and that is called as Coulomb's constant. So what we can observe from this Coulomb's law, that the force or the electric force is always directly proportional to product of both of the charges and inversely proportional to square of distance between them. That is nothing but inverse square law, right? That F is directly inversely proportional to 1 upon R square. So if there are number of charges present, Q1, Q2, Q3, Q4 up to Q1, how will you find out force acting on Q1 due to Q1, Q2, Q3, Q4 up to Q1? The force applied on Q1 because of all of the charges will simply can be find out using superposition of forces. If there are more than two charge objects interacting with each other, the net force on any one of the charge object is vector sum of the individual Coulomb forces on that charge object, and that is nothing but superposition principle. You just have to add all the individual Coulomb forces. Let's say the example, if there are three charges present, Q1, Q2, Q3. Okay, so the distance between Q1 and Q2 is, let's say, R2, and the different distance between Q1 and Q3 is, let's say, R3. Okay, so the Coulomb's force exerting on Q1 because of Q2 will be K Q1 Q2 upon R2 square, right? And the second force, that is due to Q3 will be K Q1 Q3 upon R3 square. So the total force acting on Q1 will be, just add both of them. It will be K Q1 Q2 upon R2 square plus K Q1 Q3 upon R3 square. So you just have to add them, and that is superposition principle. For a system of charges, we always apply superposition principle. Let's see the next topic, that is electric field. So we say that when a charge object is put in a point in space, the charge object sets up an electric field throughout the space surrounding the charge object. That means if there is a charge Q, right? There is an imaginary field around it, and that field is electric field because of that charge. This field then exerts a force on another charge object, and we have seen that force in last slides. Which was this force? Yes, this was electric force, or we can also call it as Coulomb's force, which was denoted by the formula K Q1 Q2 upon R square, right? So whenever charges are present, and if we bring up another charge, it will feel a net Coulomb force from all the others. It is convenient to say that there is a field there equal to the force per unit positive charge, right? So let's say if this is a charge Q1 and this is a test charge Q0. What is test charge? Test charge has two properties, that it is always positive in nature and it does not exert its own electric field, or it does not exert any force on another charge, right? So when Q0 is placed near Q1, this Q0 will experience some kind of a force because of this Q1, and that force is because of the electric field. There is an electric field, right? So what do we define electric field? That force exerted on that Q0 charge, and it is given by F upon Q0. The direction of this electric field is along R. That means this distance, along this distance, and points in the direction of positive test charge towards this. Okay. So yeah, here we can see the direction. Okay. And the Coulomb's force is given by F is equals to Q1 Q0 upon R square. So that is why E can be given as F upon Q0. So when we substitute F in this equation, what will you get? E is equals to K Q1 upon R square. And this is due to point charge Q1. So the SI unit of electric field is Newton per Coulomb, and the electric field has a direction. That is why it is a vector quantity. How will you find out the direction of electric field? So the arrow will show. This arrow is showing the direction of electric field. It is away from the positive charge, right? And it is on the vector R. Okay. Yes, if Q1 is positive. What if Q1 is negative? Then this arrow will be in negative opposite direction. That means towards this charge Q1. So electric field lines. What are electric field lines? These are the imaginary lines in the region of space-time. They originate from positive charge and terminate at negative charge. They do not form closed loop, as they are originating from positive charge and terminating on negative charge. So how will they form a closed loop, right? And as they are not terminating in space, that means they will continue till infinity. And the number of field lines are directly proportional to magnitude of charge. More is the magnitude of charge, there will be more field lines. And if there are less is the charge or the magnitude of charge, the number of lines will be less. These are some examples how field lines can look. For a point charge, that is for positive point charge, the electric field line should be radially outwards. What if this positively point charge, if this positive charge can be replaced by negative charge, these lines will get radially inwards. Okay. Now, if we consider one negative charge and positive charge, what will you observe? That these field lines are originating from positive charge and terminating on negative charge. So, from positive charge, the electric field lines are always directed radially outwards, whereas for a negative charge, the electric field lines are always directed radially inwards, right? If we bring both of the positive charge together, what will you observe in the space between them? That means this area will always remain empty. Why? Because these both charge tends to repel each other. So electric field lines will also repel. Okay. What is electric dipole? Electric dipole, the name says it all. Dipole, right? Poles apart. So if a pair of point charges having equal magnitude but opposite direction, that means there is a pair of charges. One is positive Q and second one is negative Q. Both should be Q. That means both are having same magnitude but opposite in sign. And they both are separated by some distance. Let's say this distance is twice A. For our convenience, we are saying this distance is twice A. So, if we consider two equal charges but are oppositely signed, that means one is positive charge and second one is negatively charged, and they are separated by some distance twice A. This system is called as electric dipole. Here is an example of that. This is negative charge, this is positive charge. These both charges are equal in magnitude, whereas opposite in direction. And these both are separated by some distance. Let's say this distance is 2A. So this system is called as electric dipole. So yes, this was our first part of electric field and charges. We will see next part, in which we are going to see Gauss's theorem, applications of Gauss's theorem, electric flux, some numericals, and we will then complete this chapter. Until then, bye-bye.